Good morning, everyone. I'm joining you from Pretoria in South Africa, where we just had a very successful Congress of the South African Mathematical Society. So let's begin with, right, so let me first tell you that if you want to ask a question, you can just turn your microphone on and ask. Don't raise your hand because I'm joining from my iPad and I won't be able to see if you raise your hand. So we stopped somewhere with examples of categories. And what we want to do next is explore more what we can do in a general category. And then we will link this with examples illustrating various concepts and theorems. First, let us remind ourselves what a category is. But this time round, let's work with the more standard definition of a category. And I'm also going to explain how it links with the other definition we started off with. We already gave a hint on what that standard definition is at the last lecture. So a category consists of a data of three things. These are objects. Then we have morphisms between objects, which are written as arrows connecting one object with another. And in our earlier attempts to define a category, we said that the third piece of data is a set of equivalences of paths. But there is a more efficient approach to defining a category where we don't have to list all the equivalences, only some of them, and then even better presentation of that is via what is called composition. So the third piece of data in this definition is the operation of composition. So composition, what is composition? It is an operation. It combines two morphisms, let's say F and G. Now it must be so that the codomain of F, so the objects to which F points, must be the starting point, or in other words, domain of G. And then when we have such a pair, then it combines this into a single morphism. And that single morphism must start with the starting point of F and end with the ending point of G. So its domain will be X and the codomain will be G, and it will be written as G circle F. So it combines such a pair of morphisms into a single morphism. And this is something that happens for every pair FG. So for every pair FG, we should have this third morphism that's defined. And it is part of the data rather than part of axioms, because we could have many different ways of choosing what this would be. So we have to make one choice, and then we get a category. If we make it a different choice, we might get a different category. However, there are some conditions still that need to be satisfied by this data. So a category consists of these three data, and then the following axioms must hold. What are these axioms? Well, first one is called associativity, and I'm going to make a drawing for it. Let's say we have F, G, and H. By applying the composition operation, we could form G composed with F, right? And then by applying it again with H, we could form H composed with G composed with F. But we could also do it the other way around. First form H composed with G, Oh, I don't need those brackets there, sorry. Let me take them off. And then form H composed with G composed with F. Now the axiom says that these two composites, the ones with three morphisms in it, must be equal. So associativity requires that H composed with G composed with F is always equal to H composed with G composed with F. So that's our first axiom on a category. We also have a second one. And the second one says that it's called the identity axiom. It says that for every object X, for every object X, there must exist a morphism from X to X, and we will call this special morphism one with X as a subscript. So such a thing must exist, which further must satisfy the following. So there must exist this identity morphism, that's how we call it, such that F composed with identity is always equal to F for every morphism F that goes out from X. And at the same time, identity composed with G must always equal G for every G that goes into X. So that would be a G that goes, let's say, from W to X. So you see, we don't necessarily require these identities to be part of the structure because we will actually prove that such morphisms will always be unique for every given object X. So we put it under the axiom. However, we can't do the same thing for composition because we can have, for the same data of objects and morphisms, that would be a graph, right? We can have different ways we can define composition. Now, the way this links to the definition of a category we gave before is that once we have this data, we can define equivalences of paths of morphisms quite naturally. And this is how we can do that. In a category, if I have two paths of morphisms, let's say given by F's, I'm not labeling the objects in the intermediate steps for now, given by F's and given by G's. So we will consider them to be equivalent when composing these morphisms in each path. So there are many brackets here. Gives the same morphism. So this composite of the F's must equal to a similar composite of the G's. Ran out of space to draw the bracket. Let me go back. So there we go. I hope my screen is still visible, right?
Yes, it is.
Now, what are these things here on the left and on the right? Well, if I expand my drawing of my path, and I can explain what they are. So let's say I've got a path of h1. Let's say this is x0, x1, h2, x2, h3, and so on. It goes all the way to, let's say, xn via hn. I can form the composite of the first two. Actually, that's not what I did in the previous picture. So let me show last few terms of this series. So let's say this is hn minus 1, xn minus 1, and then we have hn, xn. I can form this composite, hn composed with hn minus 1. And then I can compose that with the morphism that's right before that. So I'll form another composite. And eventually, so I go on like this, and I form this composite. Then that is the last blue arrow, then is composed with h2, then I get this one. And then it composed with h1, and then I get that one. And that's what this long expression here represents, but of course for f's. And we've got something similar here for g's. But because of associativity, because of this rule, which tells us that the order in which we compose these morphisms in a path, but now this is for a path of just 3 morphisms, the order doesn't matter. You see here we compose these two first, and then we compose that with h. But that was required to be the same as composing those two first, and then composing that with f. And the effect of that is that even for a longer path, such order wouldn't matter. So for instance, if I had something of length 4, let's say I've got my h path being of length 4. So h1, h2, h3, and h4. If I form the composite h4 composed with h3, composed with h2, and then composed with h1, that will be equal to any other way of ordering this composite. So of course I cannot change the order of h's themselves, but I can change the order in which composites are formed. For instance, that will equal to let's say h4 composed with h3, composed with h2, composed with h1. And it's not difficult to see why this will be the case. You can apply associativity first inside here. So you will get that this is equal to h4 composed with h3 composed with h2, and then the whole thing composed with h1. And then you can treat this as a single morphism, because it is. Composite is a single morphism. And then apply associativity for these 3. And if you do that, you will get exactly what we've got here. And so you see, I've got 2 ways of putting brackets on these 2 sides, and the expressions end up being equal. And in fact, the same is true if I have any longer composite, and any ways of arranging brackets, any 2 such ways will always be equal to each other, and that I can deduce from the associativity axiom. So knowing that, I no longer have to worry about brackets when I write composites of morphisms, because the answer, the value of the expression, is independent of how we put brackets. So we don't have to put the brackets at all. And then I could rewrite this as fn composed with fn minus 1 composed with all the way, composed with f1 equals gm composed with gm minus 1 composed all the way, composed with g1. Okay, I'm going to, at this stage, turn on my camera and wait for your questions if you've got any.
Yes, I do have one. Good morning, Prof.
Good morning.
You mentioned something about not requiring the identity to be part of the structure. Can you elaborate more on that one? I think I missed something.
So thanks for the question. Before I elaborate on that one, did you understand what I tried to explain here with the brackets?
Yes, I do understand the associativity part.
Okay, great, thank you. So you see here, we do require that for every object, the identity exists, right?
Yes.
But one might think that, okay, maybe for every object, there are multiple such morphisms making these always hold. That could be potentially possible, right?
Yes.
So if there is multiple choice of identity morphisms, then which one is denoted by 1x? And if I change my notation, if I change the identity morphism from one to the other, will I get a different category? It's like, imagine, for instance, there was multiple ways of composing things, and they often are. If I change my composition, I will get a different category.
Mm.
But here, it turns out that there isn't multiple ways to have identity morphism. So it will turn out, and we will prove this now, it will turn out that for every x, there is exactly one morphism. When it exists, there is exactly one morphism that makes those two things true, this one and that one. And so we don't have to worry about choosing which one to pick, because there is always one, exactly one. And because of that, we don't have to specify it as part of the structure, because it's uniquely determined.
Oh, okay.
Like, let's say when we define a vector space, right? Many
Yes.
textbooks say, consider this set, and then they say, this set is a vector space. Let's take R cross R, set of ordered pairs of real numbers. You will find many textbooks say the set R cross R is a vector space. Now, this is a very incorrect, logically incorrect thing to say, because a set alone doesn't know how you're going to pick your addition and multiplication and scalar multiplication. There could be many ways of picking. So when you say that a set is a vector space, it doesn't give us information, much information. It just tells us that there is some way of defining addition and there is some way of defining scalar multiplication that turns this set into a vector space. But I have to pick a specific way before I can work with it as a vector space. But then the textbooks don't do that. They simply continue assuming that the vector space they have in mind is the one where vector addition that is done component-wise and so on. And so then they mislead the reader as if the set already has the structure. It does, but there are many other structures. And so when you pick to work with one, you have to say that. So here we don't have to say that we're going to pick with certain identity morphisms, because there's only one choice of identity morphisms. Does that make sense?
Yeah, it makes sense now.
Fantastic. Any other questions? I think I can leave my camera on. Brendan, is it okay? Do you think it looks good? It's not a weird angle.
No, it's fine.
Okay, fantastic. I thought I would be writing on my lap, but somehow I ended up writing in such a way that it works. Okay, so when we define equivalences of paths this way, we're going to get something that is a category in our previous sense. So let's recall that previously we defined a category as a data of three things. These were objects, in other words, the set of objects or class of objects, morphisms, and equivalences. And now we're defining a category as a data of objects. Are we back? Hello?
I think you're back, but the feed has gone.
So what happened is that my iPad started complaining that it was overheating and it needed to cool down. It's very hot in Pretoria. Let me see if I can go back to Zoom to share the screen again. I think I'm not going to use the probably the camera adds to the workload. Sorry about that. So, but wait, where is the program for drawing that I used? There we go. So you can see the screen now, right, Brendan?
Yes, it's come back.
Yes.
So previously we defined a category as a data of three things: objects, morphisms, and equivalences. We're now going to call that kind of thing a slightly different name to distinguish with the category we defined today. So henceforth, we will refer to our previous notion of a category as we will refer to our previous notion of a category as a cat. Just to distinguish it, the one we're discussing today. So cat is something we are all quite familiar with, right? It has more or less this kind of shape. But of course, the cat we have in mind here is not this cat. It's a data of objects, morphisms, and equivalences rather. And let's also remind ourselves that this data needs to satisfy certain axioms as well. So it must satisfy E1 up to E6. But we're not the first one to draw a category as a cat. This is a well-known tradition in category theory. You'll find some books, at least one, but I think there's more than that, where the pictures of cats appear in the book of category theory. Okay, so the link between these two notions is the following. By defining equivalences as of paths in a category in the new sense, the way we did above, when we said that the composites of morphisms in the path must be equal, we get a cat. So it turns out that the axioms E1 to E6 are satisfied. We're not going to go into that now. We kind of discussed it in an implicit way. I think we mentioned it a few times during the lectures. But then the other way around is also true. Conversely, given a cat, we can define composition as follows. We can define composition by saying that if I've got two morphisms, F and G, in a cat, the axiom of reduction forces us for there to exist a morphism, H, that is equivalent. So there exists H that is equivalent to the path GF. So this is the path, right? or actually we were calling it FG rather than GF. So we know by reduction axiom that for any path FG, there exists H that's equivalent to that path. And then we can further claim that there will be only one such, because imagine if there was another one, let's call it H prime, that H prime would be equivalent to the path FG. Now, by symmetry, FG path is also equivalent to H because H was equivalent to FG. And then by transitivity, we get that H prime equals is equivalent to H. And then by axiom of equality, which E is that? I think that's E6, I think. We can conclude from here that H prime equals H. So we can then define H, the composite, as the unique morphism. You see, it's unique because H always ends up being equal to H prime. So we can define this as the unique morphism such that as a single morphism path, this is equivalent to the path FG. And then it will turn out, and again, this is something we already implicitly established, it will turn out that this way of defining composition does define a category. Let me just separate this text from each other to make it more clear what's going on here. So conversely, given a cat, we can define composition this way, and this will turn a cat into a category. And so we have this this process of moving back and forth between a cat and a category. So if I draw here categories on one side and cats on the other side, right? Every category gives rise to a cat. Every cat gives rise to a category. And in fact, it's not difficult to see actually that also this process are invertible. I mean, they're inverses of each other. So if I create a cat out of a category, and then I create a category out of that cat, I will get back my original category. And the same is true on the other side. If I create a category out of a cat, and then I create a cat out of that category, I will get back my original cat. So these sets of the classes of categories and cats, they're in bijection. And that means that the concept of a category is equivalent to the concept of a cat. That's how we can intuitively express that. But certainly, a cat is a less efficient way of describing this concept because it has more data. There are more equivalences than compositions, because equivalences can be between arbitrary paths of arbitrary length, whereas compositions are kind of equivalences of special sorts. So they're kind of equivalences of this sort. And so it is better to work with categories when we want to, at least when we want to prove something is a category, because then we have to build less structure. We don't have to build all the equivalences, we can just build compositions. But on the other hand, the usefulness of cats is that when we want to create examples of categories from real life or from mathematics, it is much more intuitive to think of equivalences of paths in some sense than of composites. And so when building examples, this approach of cats is could be a bit more useful than the other one. But from this point on, we're going to work with categories in this new sense that we introduced today. Any questions on this before we move on? Somebody should give me a go ahead so that I know that it's all good and we can proceed.
I think we're fine.
Okay. Great. Now, let's recall from the previous lecture that we had this concept of an isomorphism. Oh, sorry. Before we do that, let's prove this thing we said that identity morphisms are unique. So let's call this the theorem. If I've got a morphism, let's say E, it's a morphism such that with E always equals F. So any F. And also,
Observe, something's gone strange with your audio.
is it better now?
Yes.
So let me repeat. If E is a morphism such that F composed with E equals F for every F, and also when I say any, I mean every. So let me rather put every here. I think it's more clear what that means. And also, E composed with G equals G for every G, let's say from W to Y. So if E is such a morphism, then it turns out that E will equal to that identity morphism that has been randomly picked in the axiom of identity. So then it turns out that E equals to that 1x. Remember, 1x was a morphism that had that property by the identity law. And now if I pick any other morphism with the same property, it will necessarily be equal to that, the one that we spoke of in the identity axiom. So any two such things are always equal, and hence they're unique, because existence is guaranteed by the axiom, and now this theorem will tell us that they're also unique. The proof of this theorem is quite simple, and at the same time quite non-trivial when you do it for the first time. So I would really like the audience to engage on this. Yes?
The domain, the code domain of G and E, today,
Yeah, I made a mistake there.
Proposition?
I made a mistake there. Thanks for picking that up. G shouldn't be from W to Y. G must be from W to X. Thank you. That's what you meant, right?
Yes.
Fantastic. Thank you very much. So let's see how we can prove this. And I would like those of you who haven't seen the proof of this before to suggest me some ideas. What do you think we should do? Just checking the chat here. Okay, great. No questions there. So what do you think we should do first? I mean, from the offset, we don't know how to prove this theorem, so we have to discover it. And when you want to discover something in mathematics, what is the first thing you do before you discover something? Sometimes you don't discover. Sometimes it's very difficult to discover something. You never discover it. But sometimes it's not so. And when you do manage to discover something, what's usually your starting point? You see, our mind needs to have something to reflect on. And a bunch of words is not usually very useful. Better to have some drawings. So let's write down and reflect on everything we know. If you want to prove something in mathematics, usually, and actually always, what is a proof? A proof is when you derive some conclusion from some assumptions, right? It's like going from one place to another. and you want to catch your taxi when you go from one place to another. So how do you catch taxi? You need to be observant of the cars that are driving past you, right? If you just look into the sky, all the taxis will pass you, you'll never catch a taxi. So you have to be observant of what you've got in front of you. And that's exactly what we should do here. So let's be observant of what we have, what assumptions we have, so we can maybe discover how to derive the conclusion we're looking for. So what do we have? Well, firstly, we have this guy here, identity morphism, which has this property that every time I compose something with it on one side, it equals that thing. Sorry, not identity, it equals f. And also, it has the property that every time I compose another thing with it, on the other side, it still equals that other thing. And this is true for every f and g, as long as of course f departs from identity, otherwise this composite wouldn't make sense, and g goes into, I didn't mean to say identity, sorry, I meant as long as f departs from x and g goes into x. So that's for every f and g. Now, another thing that we've got is that we have this emap, which has similar properties. So again, for every f, f composed with e equals f, and e composed with g equals g. So this is true for every f and g. And now we want to see how we can derive from this, right? From these two things, we want to derive, and usually in logic one puts this beautiful horizontal line to indicate you want to derive something. So the question is how to derive that. And what we want to derive from this is that E equals identity. Now, basically, if you reflect on this, we've got a bunch of equalities, and we want to derive from it another equality, except that the first set of equalities we've got here, it's not just, sorry, I meant to highlight that. So the equalities we've got here is not just 4 equalities, there are infinitely many of them, potentially, because f and g can be arbitrary morphisms. Now, when I have a set of equalities and I want to derive another equality from it, what's the technique we often use? Try to apply that technique. What do you think we should do? What do you think we should try to do? I mean, we still don't know how to get to this conclusion. We don't know how to get here yet, but we want to explore a bit what we've got here, and what would be a first step of such exploration. Now, I said that those who haven't seen this should be the ones who answer my question, but maybe everybody has seen this. So let me just double check that there's actually someone who doesn't know how to do this. Is there such a person in the audience? Doesn't seem like it, right? Nobody's saying anything. Maybe somebody put something in the chat. Brandon, can you please check if anyone put any message?
No, nothing in the chat.
Okay, maybe everybody indeed has seen this. So the equalities we've got here and here. The top one involves only identity, the bottom one involves only E. We want an equality that involves both, so we somehow want to maybe create an expression which involves both E and identity. And there's one simple way of doing that, since this can be applied for arbitrary f and g, and also these can be applied to arbitrary f and g. We could take specific f and g, So specifically, we could take the f to be the other thing that we want to be the expression. So for instance, in the first set of equalities, we could substitute f to be e, right? So we then get e composed with identity x equals e, and identity x composed with e equals e. On the other hand, downstairs, if I substitute the other one, identity in the place of f, I get identity x composed with e equals identity x, and e composed with identity x equals identity x. And after this, I think it's quite straightforward. So we notice that this expression, for instance, right here, is on one hand equal to e. On the other hand, it's also equal to the identity x. And therefore, the two things are equal. So my proof is basically a single line. E equals e composed with identity x by this rule. And then that further equals identity x by this one. Any questions on this proof? So this was our rough work.
So as far as I understand, we don't need identities to satisfy this equation for all possible, so to say, morphism, but just for endomorphisms, right?
That's a good observation. That's a very good observation. If we, so you're saying that we can generalize our theorem. We could say that some kind of weak identities are still unique, where a weak identity is defined so that the equalities hold, these equalities hold only for f and g, which are endomorphisms. And that would be true because, as you correctly remarked, our proof is also valid in that case. Would be actually interesting to see an example of graphs with composition, with associative composition, where the normal identities don't exist, but these weaker identities exist. I actually don't know an example like that for now. It never, the remark you're making never occurred to any category theories before, I think. Even though, of course, it's quite obvious remark, but nevertheless, one hasn't thought about this before. So you might want to think of an example that illustrates the usefulness of this weaker notion. Any other comments or questions? I mean, there is also another remark we can make. For instance, we only used this and that, and so we use the fact that identity is right identity in the sense that you write it on the right and then equality holds. And here we use the second one, you use the fact that E is left identity. So it's another way of generalizing. And then we can generalize both further by saying the same, but now just for endomorphisms again. Okay, so we know now that identity morphisms are unique. That's all good. And now let's look at the notion of an isomorphism. And after that, we're going to look at some categories that arise in algebra. Okay, so we already had a definition of isomorphism in the previous lecture. Let's just remind ourselves what that was, but it was in the context of CAD, so maybe it's useful to rewrite it in the context of categories now. In a category, an isomorphism is a morphism f, let's say from x to y, such that there exists morphism G from Y to X with the properties that G composed with F. I think my iPad is heating up again. If it interrupts for a moment, please forgive me. G composed with F equals the identity of X, and F composed with G equals the identity of Y. Now, an obvious example of an isomorphism is the identity morphism, right? Maybe we should call this a theorem rather than an example. Every identity morphism is an isomorphism. What plays the role of G for an identity morphism?
Itself.
Itself, that's right. So the proof is rather straightforward. Identity composed with identity equals identity, and that takes care of both this one and that one. By the way, this G is called inverse of F. Let's write this in here. G is called inverse of F, and so identity is inverse of itself. Now, the concept of an isomorphism is very fundamental in mathematics because so remember that the morphisms were some kind of processes, and when our objects are mathematical structures, the morphisms are transformations of these structures. Now, an isomorphism is a morphism where you can transform one structure into another, and then you can transform it back without any kind of modification or loss or gain of information to the original structure. And this happens on both sides, on the left side and the right side. So it kind of tells you that the two structures are basically essentially the same thing. And to illustrate that, let's look at examples of isomorphisms in some algebraic categories. So well, maybe we should first talk about matrices, because that's something we introduced last time. In the category of matrices, where objects are natural numbers and matrices are of dimension that come from the domain and the codomain. So morphism from n to m is an m by n matrix. In matrices, isomorphism.
I have a question. Yeah, so I want to know regarding the concept of isomorphism.
Yes.
If we have a category,
Yeah.
and we have several objects in the category. Is it always the case that if an isomorphism exists between, let's say, any two objects, then does it mean that the isomorphism exists between every object in the category?
So let me clarify what your assumptions are. So you're saying you got a category, right? And then you said something about isomorphism. What do we know about that category? Can you repeat that? So
let's say there is an isomorphism that exists between two objects within the category.
Okay.
The category has several objects, and there's an isomorphism that exists between two objects, let's say X and Y, for example. So my question is it always the case that isomorphism will exist between every other object within that category?
No, look, like for instance, let's take this example. Let's say we've got a category where F and G are isomorphic to each other. Sorry, where F and G are isomorphisms and inverses of each other. So let's say we've got the situation where a composite of G and F equals identity of X, and composite of F and G equals identity of Y. And we also have a third object Z. It only has identity morphism. There's nothing else in this category, just these morphisms. This is actually a valid category. And so you can see that even though X and Y are isomorphic, it doesn't mean that every other object is also isomorphic to these X and Y, because that isn't. Is that what you're asking?
Yes, kind of something like that. So now, can you say that isomorphism exists in the category, or will you just be specific and say isomorphism exists between those two objects, X and Y?
The second.
Okay.
And you can
Okay.
also have, and you can also have many isomorphisms between two given objects. There could be many ways of building isomorphisms. Here is an example. Okay, so I will mention this example. Just before I do that, let me just remark that in the category of matrices, where composition is given by matrix multiplication, isomorphisms are invertible matrices, and this should be obvious because well, first of all, identity morphisms are identity matrices, and then you can see that this tells us that the product of two matrices is identity, and that's exactly what defines an invertible matrix. But now, to build a situation where we can have, well, already in that example, we know that we can have lots of invertible matrices, right, of a given dimension. So, in fact, in this category, all isomorphisms are always loops. They go from an object to itself, and you can have many of them. So, so if I take, let's say, number 5, I can have a 5 by 5 invertible matrix. That would be an isomorphism. And I can have many invertible matrices of dimensions 5 by 5. All right. So Clinton, did we answer your question? Are you happy with the answer?
Not quite so. So I think my question is about the general collection of all of those objects. Yes, the general collection of all of the objects. When do we say that a category is isomorphic, for example?
Never. We never say category is isomorphic. The expression category is isomorphic doesn't make sense. Category is isomorphic. This expression doesn't exist.
Okay.
We can say one category is isomorphic to another one.
So maybe he's talking about groupoids.
Well, maybe. Let me first say what I was going to say. So we can say that one category is isomorphic to another one, but that would first require us to define morphisms between categories, which we haven't done yet. Another thing that can happen is that every morphism in a category is an isomorphism. Such a category is called a groupoid. But just this expression, category is isomorphic without anything else, that doesn't exist. Does that answer your question, Clinton, or you have a further question?
A further question. And I think it is about, okay, so let me put the question this way. If we have X, Y, Z, W, and then we want to describe isomorphism, because I understand that a category can have several objects. So let's say we have we have infinitely many objects within this category.
Okay.
And then we want to describe isomorphism within the category. So my question is, we cannot make a general statement about, okay, can we make a general statement about isomorphism within that category, or every time we talk about isomorphism, we have to talk about two objects, two or more objects within that category? We have to restrict our idea of isomorphism to two or more objects within the category, and not the general category.
So remember, isomorphism is a special kind of a morphism, right? A category has many objects and many morphisms, right? So let's make a drawing. A category has objects and it has morphisms, right?
Yes.
Now, isomorphisms are some of these morphisms. So some of them are special morphisms. I'm representing them as red morphisms. They are isomorphisms. And what makes them isomorphisms is this thing that there is something backwards, so that the composites on both sides are identities. So an isomorphism is just a special kind of a morphism. Does that help?
Yes, it does.
You got a further question?
No. This clarifies my doubt. It answers my question, because I wanted to exactly know that, okay, isomorphism in the concept of objects like the example you gave. Isomorphism is a special kind of morphism between two objects. Yes, so that answers my question.
Fantastic. Thank you very much. So let me underline this part of the definition where we said an isomorphism is a morphism F. And every time we have this construct in the definition, in a mathematical definition, what we mean by this is that an isomorphism is a special type of morphism. And the type of morphism that isomorphism is given by the condition that there must exist a morphism G such that these things hold. Fantastic.
Great.
Is that morphism G unique?
Yes. Sorry, say it again.
That morphism G, the one that needs to exist.
Yeah. What about it?
It's unique.
Let's prove that it's unique. That's a good question. That's an excellent question. Let's interrupt our discussion of examples and let's first prove that it's unique. For matrices, we know it's unique, but it's also true for a general category. Every isomorphism has a unique, maybe I shouldn't say A here, as unique inverse. Proof. So let's say F is our isomorphism, right? And we've got also G, one of the inverses. And we know that G composed with F equals identity of X. And we know that F composed with G equals identity of Y. Now let's assume that G be another inverse. Let G prime be another inverse. So that we have G prime composed with F is also identity, and F composed with G prime is also identity. Then, so we want to prove that G is equal to G prime, right? So this is what we can do. We can express G as a composite of G and identity of Y, right? And then we can, if we look at our assumptions, right? We can substitute in the place of identity of Y. We can, let's say, we use this. We can substitute F composed with G prime there. So this will give us G composed with F composed with G prime, right? But now we can use associativity to move around this bracket. So I will have G composed with F and then composed with G prime. And on the other hand, What do we know about G composed with F? Well, that's one of our assumptions as well, right? It's equal to identity. So we get identity X composed with G prime. And of course, by the identity law, this gives me it's equal to G prime. So we have a chain of equalities connecting G with G prime. Therefore, G and G prime must be equal, right? Is this proof clear to you?
Yes. So in a category, there could be many isomorphisms, but each isomorphism have a unique inverse, right?
Fantastic. Yes.
All right.
Yes, absolutely. One of my favorite isomorphisms is, and I say my favorite because it's a very useful isomorphism in real life. It's one of the most useful isomorphisms in real life. In the category of sets, so set is the notation for the category of sets, objects that are sets, and morphisms are functions. The electronic notes already has a chapter on that category. You might want to look it up if you're not quite sure what it is. But we're going to take a specific function now. So take this function from R to R plus, the exponential function x maps to e to the x. So in other words, define f of x to equal e to the x. Of course, looking at the graph of e to the x, we know from the graph that this will be, you see, any horizontal line I draw here to only overlap the graph at exactly one point, right? It kind of shows you that it's a one-to-one correspondence. And in fact, the inverse of this isomorphism, who knows what the inverse of f is?
ln x.
That's right. The inverse of this is the natural logarithm. And why this is so? Well, first of all, G is defined on all of R plus. And of course, graphically, this means that the graph is flipped. And so G is defined from R plus to R. And then the composites, so I take F composed with G. I now want to get convinced that this is equal to identity, right? So I evaluated it at random x. This is the same as F applied to G of x. That's how we compose functions, right? What is G of x? G of x is ln x. So this is the same as F of ln x. What is F? F is exponentiation. So e to the power ln x. And of course, we know that e to the power ln x is x. And the other way around? Okay, first this shows that F composed with G equals identity of R, right? Not of R, sorry, of R plus. And also, we've got the other way around, because G composed with F applied to X, same as G of F of X, that's the same as G of e to the X, that's the same as ln of e to the X, which is the same as X. And so G composed with F equals identity of R. So that's an example of an isomorphism. It's a very familiar example, and it's also very useful because when modeling real life, using differential equations, for instance, to make predictions and so on, the function e to the x comes up a lot. And the fact that it has inverse is also useful. Sometimes you transform your differential equations by applying this isomorphism and solve the transformed equation, and you transform back by applying the inverse. It's one of the ways that this invertibility is used. Any questions on this example? Is my voice still clear? Because there's a bit of conversation in the background.
Yes, it's fine.
Okay. Now, let me see what where we were at. Yeah. So let us look at some. Sorry, I'm going back and forth here. Let us look at some more examples of categories, and we explore what are isomorphisms there. Okay, I'm trying to find my way here. Right. We can create categories out of algebraic structures. Let's first list some examples of algebraic structures we know. So each of you, please name an algebraic structure to be inserted in our list, an algebraic structure that you're more or less familiar with.
Groups.
Did somebody say groups?
Yeah.
Okay, groups is one algebraic structure. Another one? Someone else?
A monoid.
Monoids. Anyone else?
Fields.
Fields.
And maybe rings, so it's more interesting, I suppose.
You can put rings as well. Any other ideas? What about vector spaces?
Lattices.
Lattices. Last one.
Modules.
Modules over a ring. This is a special case. I mean, vector space is a special case of this, where the ring is a field.
So maybe algebras as well.
Algebras over a ring. Yeah. There are, in fact, a lot of examples. There are many, many different examples. Some of them are closely related to each other, like rings and fields. Others are quite diverse from each other. Like lattices, for instance, are quite different from fields, for example. Now, there is something all of these have in common. They are all specified by data consisting of a set and a bunch of operations defined on it. Let's make it explicit in each case. What are these operations? In the case of groups, we've got a set X, and it has a binary operation of multiplication. So it's a map from X cross X to X. Now, we could also include in the data the identity elements in a group and the inverse elements, but we don't have to because they're always unique when they exist. So just like in the data of a category, we didn't specify identity morphisms, we had them only in the axioms. In the same way, a group can be more efficiently defined using just a single binary. The axioms will also involve existence of inverse elements and identity elements. A monoid has a similar structure. A monoid is also a set with a binary operation. A field is a set with a binary operation of multiplication, just like the other two, but also a second binary operation of addition. So a field has two binary operations. The same goes for a ring. A ring has two binary operations as well. One of them is denoted by multiplication, the other one by plus. Now, what about a vector space? How can we view a vector space as a set equipped with a bunch of operations? Well, vector addition is easy. It is a binary operation. But scalar multiplication is something funny, because for scalar multiplication, you multiply element of the field over which your vector space is. Let's say we've got vector spaces over real numbers. You multiply a real number by a vector. So it's not quite an operation, a binary operation on X, because the real number doesn't necessarily come from X. But how can we still present a vector space as a set equipped with a bunch of operations? Any ideas? So the trick is to view multiplication by a fixed scalar as a unary operation. So we have a family of unary operations, one for each scalar R. So there is a single binary operation and a family of unary operations indexed by real numbers. So there is a single unary operation for every real number. Does this make sense? Everybody's happy with this?
Looks like it.
A lattice is a set, thanks Brandon. A lattice is a set with two binary operations. They're called meet and join. Again, the rest of the lattice structure can be, well, actually in the lattice we don't really have any more structure, just these two. So there are two binary operations, meet and join. What is a module over a ring? It has an exactly similar structure to a vector space. So we've got addition. And then we've got a family of unary operations. So what I mean by this R dot blank, blank being written by a hyphen, is that this blank is the placeholder. So you map X to R dot that X. So X takes the position of the blank in the mapping. And this is one for every element of the ring. In an algebra over a ring, and many of you might not know what an algebra over a ring is, but it doesn't matter. For now, we're not going to go deep into that. Just to show the structure for those of you who know what an algebra is, it has a binary operation of a plus, and it also has a binary operation of multiplication, in addition to being a module. So these two will actually make it into a ring. And then there is still a module structure given by this family of unary operations. So R is now my ring over which I have algebra. So you see, in these examples and in many other examples of algebraic structures, the structure is given by data consisting of a set and a bunch of operations defined on it, where an operation is a map from some Cartesian power to that set. So let me write this down. A common feature of algebraic structures And these algebraic structures are called single sorted. Otherwise, if I had more than one set, like here I only have X, but I could also have X and Y. Then I would call it two sorted or n sorted if there are n many of them and so on. In this case, it's single sorted. The common feature of single sorted algebraic structures is that they are given by a data consisting of a set X and a family of operations on X. Here, by an operation, oh dear, they turned music on. This will probably mean I have to move. Can you still hear me, or the music is too loud?
Yes, you're clear for me.
Okay, that's good. Here, by an operation, we mean a function, let's say P, from X cross X cross X, where X is n many times. A function from there to X, where n is called the arity of the operation. You can really think of these operations as some sort of generalized polynomials. N is called the arity of the operation. For example, when n equals 1, we get unary operations. These will be just maps from X to X. And when n equals to 2, we get binary operations. So this will be from X cross X to X. Now, having made this remark, we can develop a universal method for building categories out of algebraic structures of the same kind by defining a homomorphism of operations. So given two operations of the same arity, let's say n. So the two operations are, let's say P. It's an operation on, there's a short way of writing this X times X n many times. So it's written with X to the power n. For the same arity n, okay, yeah, where we are. Okay, so, sorry. So if I have two operations, one defined on a set X, and the other defined on, let's say, set Y, a function f from X to Y is said to be homomorphic with respect to these operations when the following holds. And this must hold for all values x1 up to xn in X. So if I first operate on my values, and then apply my function f to the value to the result of its operation, this must be the same as first taking first mapping the elements x, y up to xn by the function f, and then applying the operation we have on y. Brandon, can you still hear me? The music is not too disturbing?
No, no, it's fine, Zero.
Okay, great. Is this concept clear? So we can illustrate this on an example. Let's say we've got plus. Let's say our two operations are plus. So this is our P, and multiplication is going to be our Q. Now I'm only considering multiplication over non-negative reals. So let's say this is our Q. Then the function e to the x, right? Fx equals e to the x is homomorphic. Why? So if I look at the previous expression, I need to evaluate my f at what? At p of x1, comma x2, right? But what is p of x1, comma x2? P is addition, right? So this will be f of x1 plus x2. But what is f? F is exponentiation, so this will be e to the power x1 plus x2. And of course, we know that this equals e to the power x1 times e to the power x2. But e to the power x1 is nothing other than f of x1, right? So we get f of x1 times f of x2. On the other hand, times is our function, is our operation q. So we can rewrite this as q of f of x1, f of x2. And you see, we get this homomorphic property in this example. But this idea can be now applied to arbitrary pairs of operations. And then this allows us now to build categories. But before I build a category, I want to ask you if it is clear, if this concept of a function being homomorphic is clear or not. You can ask some questions if you have about this. Questions? It's clear. Alexander, are you happy with this?
Totally.
Okay, so we can now build. We can now build a category from a system of algebraic, rather, let me call this not a system but a class, from a class of algebraic structures of the same type, how do we build a category? Objects are these algebraic structures. Morphisms are homomorphic functions, in other words, homomorphisms. So they're called homomorphisms. Morphisms are homomorphisms. In other words, functions f, let's say, from x to y, where x and y are my algebraic structures. So they're functions from the underlying sets, between the underlying sets of those structures. They're functions such that for every pair of corresponding operations on x and y, f is homomorphic. So let's say x and y are vector spaces, right? We have a whole bunch of operations. Then we have addition of vectors, and we have multiplication of vector by a fixed scalar. Now, being homomorphic for each of these means that f of, let's say, x plus y must be equal to f of x plus f of y. At the same time, f of r times x must equal r times f of x. And of course, in this way, we will get the usual notion of a linear transformation between vector spaces. So these are morphisms, while composition is defined by composition of those functions. So it turns out that if you take a homomorphism and you compose it with another homomorphism, this composite function will also be a homomorphism. The composition is because these morphisms were defined as special kinds of functions, right? And so their composition is defined as their usual composition of these functions. Composition is defined by composition of functions in the usual way. And now if we go back to, okay, we're not going to prove now that we actually do get a category. We just have to prove this associativity and identity law. It will not be difficult to prove them because we already know these laws hold for usual functions. Basically, the only thing we'll have to prove is that composition of homomorphism is always a homomorphism, and that's not difficult to prove either. But what I do want to do is to give names to the categories we get for the structures that we specified before. There are some standard names for these. The category of groups, where morphisms will be group homomorphisms, we get is called the GRP. Monoids is mon. Fields, I'm not quite sure, to be honest. Maybe FLD, but I don't think there's a standard notation for that. RNG, well, actually RING sometimes, if it's rings with identity. If rings without identity, then it would be called RNG. Vector spaces is VEC, and then we put as a subscript the field over which this is a vector space. In this case, we were considering real numbers. Lattices would be lat. Modules will be mod. And then again, the ring over which we have the modules will be a subscript. And algebras over a ring will be alt and R. So it happens so that all the structures you specified here are very, very important and standard structures in mathematics. And so there is standard notation for the corresponding categories. Now, let us look at some interesting examples of isomorphisms in some of these categories. Maybe not too many of them, but let's say we look at the category of text spaces. So it will turn out that isomorphisms in these algebraic categories are nothing other than bijections that are at the same time homomorphisms. If you've got a bijection that's a homomorphism, the inverse map of that bijection will also be a homomorphism. So in the category of vector spaces over, let's say, real numbers, let's build an isomorphism, an interesting one, from R cross R to R cross R. Can you think of an interesting isomorphism from R cross R to R cross R? We have to decide where we map the pair XY.
Maybe rotation.
Yeah, rotation would be interesting. The formulas would be complicated. Let me rather do something simpler. The flipping. So first of all, we want to show that this is a homomorphism, right? Well, so this is our F. Well, it is a homomorphism because the operations are preserved. So if I take a vector xy and then I add to it vector x prime, y prime, and then I apply f to it, what do I get? This will be f applied to, how do I add vectors? I add them component-wise, right? So x plus x prime, y plus y prime. But what does f do? It swaps coordinates. So we'll have y plus y prime, x plus x prime. Okay? And then we can separate the two pairs now, yx pair and y prime x prime pair. And on the other hand, yx pair is our f of xy, right? And y prime x prime pair is our f of x prime y prime. So you see we get this homomorphism property for the operation of addition, but we also need it for scalar multiplication. So if I take f of some real number times vector xy, that will be the same as f of, how do we multiply a vector by a real number? By multiplying every coordinate by that real number, right? So this is f of rx, ry. And then f does the flipping. So this is ry, rx. But now I can take the r out. It's the same as r times yx. And so this is the same as r r times f of xy. And so you see we have the homomorphism property for scalar multiplication as well. Remember, this is unary operation, so that's why r stays fixed, because it's multiplying by r seen as a unary operation. This shows that our f is actually a morphism in the category of vector spaces, but now we also want to show that it's an isomorphism. So we want to find its inverse, and of course the inverse of f will be, in fact, itself, right? So f composed with f applied to the pair xy is the same as f applied to f applied to xy. And so this is doing the flip once. And then we want to do the flip second time. But we get back then the same thing. So we can say that f composed with f is the identity of r cross r. So f is inverse of itself, and hence it's an isomorphism in the category of vector spaces. Now, this isomorphism has slightly different role to play in mathematics than what we usually said isomorphism should do. So what we previously said isomorphism should do. So previously we said, let me actually stop sharing for a moment and turn my camera on. Previously, we said that the job of an isomorphism, is to say that two structures are basically the same structure, okay? Because you have this one-to-one correspondence. In the algebraic case, it preserves the operation. It turns out that its inverse will also preserve the operation. I mean, the set theoretic inverse. So the two structures will be only different from each other up to renaming of their elements. But when the two structures are already the same, and I only have a single isomorphism going from that structure to itself, like the f we had here from r cross r to r cross r, then there's no point to say that they're the same, because they already are the same, right? So the role of that isomorphism becomes something slightly different. In fact, as you said, Alexander, the first example you wanted to be a rotation, and this one is a flipping. So it's a kind of transformation of my space. I mean, I want to see now r cross r as a two-dimensional space. It's a transformation of my space that has many good properties. It preserves distance, for instance, and we call this thing in mathematics symmetry. So symmetry on a mathematical structure is when you're transforming your structure in such a way that the structure is preserved, and including the structure of two things being different from each other. In other words, this is a one-to-one transformation. And the real-life symmetry is actually something that also gives rise to isomorphisms. And let's now draw a picture for that. Or maybe I will illustrate this with some gadget I can find in here. Let me borrow this. Oh, what happened there? Somebody turned the switched on a whiteboard. Let me turn it off. So if you look at this salt container with the salt in it, here it is. This shape you see here is very symmetric. And you can witness the symmetry by rotation. Now, observe these lines as well. There are these kind of a star with 6. What's it called? Brendan, how do we call the star with 6 things? What are these things called? What do you call the thing of the star?
Points?
Points.
Because normally you classify a star by how many points it has, right? So you would say a 6-pointed star.
Okay, so the points of the star. So there are 6 of them. Now, if I move it a little bit like this, the picture has changed because the points have moved. But if I continue moving a bit more, then now this looks very similar to the previous picture, because the position of this, so previously this second point was here, and now it took the position of what previously was the first point. And that is what we identify as symmetry of the shape, that we can do this. I can take this shape, I can rotate it and match onto its previous image. Sorry. Now this process is actually an isomorphism. It's an isomorphism of this geometric structure onto itself. It's exactly this kind of isomorphism that goes from an object to itself. And we can also think of this as the rotation that Alexander wanted initially. And so those isomorphisms that go from a structure to itself, in real life, we encounter them as symmetries. And in mathematics, therefore, they're also called symmetries. And they're very useful things. Lots of applications of these things. For instance, in the theory of differential equations, one uses these symmetries to simplify and then eventually solve a differential equation. It was an idea that was proposed by a mathematician called Lie, and in this context, the symmetries are called Lie symmetries. And so it's one of those applications of abstract mathematics that really goes back to real world, because you get these differential equations by modeling various phenomena in real world. Let me go back to sharing the screen now. So let's summarize what we wrote here. Isomorphisms between different objects allow us to view these objects as being, in a way, the same. There is something called logarithmic ruler, which makes use of the isomorphism of e to the x and ln x. This is a tool that engineers used before the time of computers. For instance, my grandparents had lots of logarithmic rulers. There were 3 of them were engineers. So we had lots of logarithmic rulers at home. And what this logarithmic ruler allowed you to do is to multiply numbers by shifting a piece of the ruler
Hello?
in relation to another piece. Can you hear me? Hello? So it had this middle piece that you could sort of shift. Basically means that you're performing addition, but because the arrangement of these things, the indicators on the ruler is logarithmic, so it takes into account this isomorphism of e to the x and ln x. Because of that, then when you read off your answer, you get the product of those numbers. So people used to multiply numbers using this ruler by performing an operation that is addition by shift. So in this way, the ruler allowed you to transform addition and multiplication. It allowed you to view them as the same. So that's an example of this idea that isomorphism between different objects allowed to view these objects as being the same. And you might want to get yourself a souvenir logarithmic ruler. Find one. Now, isomorphisms from an object to itself capture symmetry of the underlying structure of that object. Okay, so these are kind of two streams of application of isomorphisms, but there is more. There is more than just these two. A third one comes up in topology. One of the fundamental questions in topology is to understand the structure of the space, and of course this comes from real life spaces, and it has lots of applications in physics. Therefore, when you have, let's say, a cubic space, a space in the shape of a cube, which resembles the room you might be sitting in currently. This is a rather simple structure. Now, the space can become more complicated if there are some holes in the space. Let's say the space, the room has another room inside it. Okay. But you can't access that room. So now your space kind of consists of two parts, this part and the other one, the inside one. And there is no way to go from one to the other. So the structure of that space is a bit more complex than the other one. We still don't necessarily have a hole here. An example of how you can get a hole would be, for instance, if in your room you have kind of a cylindric shaped thing to support maybe the roof structure, right? And if you're now standing in front of that cylinder that's in your room, it gives you some restriction as to how you can move around. You cannot go through the cylinder, right? So if you want to, let's say, walk around your room, you might find yourself going around the cylinder, right? Now, we can form a category out of your room or the space around you by declaring the objects of this category to be positions in the space. So here is one object. Let's say here, in this example, we've got the place where you're standing, right? And maybe this one right here is a spot behind the cylinder. So let's say there are two objects, X and Y. I will have a way to get from X to Y. That will be a morphism. Then I can come back as if I hadn't left. And so this will give me an isomorphism, FG. Now, the composite of these two morphisms okay, so actually what I wanted to say is not that I can, okay, so in this case, we don't only care about the final outcome, but we also actually care about the path we travel. And the point of that cylinder is that, unlike in the case of absence of the cylinder, if your space, let us look at the whole picture from the top, okay? So there is this hole that I cannot access. So this is a no-go zone. Now, when I travel from this point back to this point, I can detect that there was a hole, that I traveled around the hole by observing that there is no way for me to continuously bring back my traveling to no traveling, because this piece here, the one that crosses the red zone, it will be impossible. So you can imagine like taking a string and so think of tying a string around that cylinder. So you're holding that string here, and it goes around the cylinder like this. And if these points are fixed, there is no way you can bring back your string to your possession because of the obstacle given by the cylinder. And so because of that, this composite GF will not be the same as identity. So in this case, F and G will not be isomorphisms, but the composite GF itself will be an isomorphism in the sense that its inverse will be itself, in the sense that if I now think of starting here, going around, right, and then coming back, if I form this longer string that starts here, goes around, and then comes back, then I can pull this end, make it shorter, make it shorter, make it shorter, and eventually liberate my string from the pole, and so the effect of that is that this GF will have a second thing going backwards that will be its inverse. So this GF will be isomorphism. And then you can start counting how many isomorphisms like this you have from X to X, and you can get many of them by taking your string and letting it go around your pole several times, your cylinder several times before you pull it back into your hand. And you'll get many of these isomorphisms here. And so the collection of these isomorphisms will be kind of detecting, in a way, that your space has this no-go zone. And this collection is actually called fundamental group of your space. And so this is a third application of isomorphisms, which allows you, by collecting them into the category of such isomorphisms, it allows you to detect the structure of your space. Just to summarize, we've got various different applications of isomorphisms, and so they're very fundamental things, even though they seem to be quite simple objects. In the future, one of the first things we want to prove about them is, for instance, that, and this is something we will do next time, is that if, let's say, F is an isomorphism from X to Y, and G is an isomorphism from Y to Z, these are isomorphisms, then the composite GF is also an isomorphism. You might want to try proving this yourself before we look at it together next time.